So the status bar contains the units, so we can easily change the units here in the status bar. So we can on or off the grip, the orthogonal, and the auto-intersect. So now in Engine, it is very easy to verify the dimensions. So first, you have to show all the grid lines. So to show the grid lines, you can right-click and then show or hide all grid sets. And then the grid lines will appear. Then under the Member tab, you click the dimension and then you click directly on the grid lines. And then the dimensions will appear. So one function that I want to show you in Engine is we can easily change the dimension of the grid lines. So for example, this one is 7,000 and I have to change it to 6,000. So I just type 6,000 and enter. Okay, and you see the columns and all of the connecting members moved to 6,000. So that's how you can easily tweak the dimension of the grid lines. So now let us confirm if the model matches with the submitted plans. Along grid line A, so we have 45, 45, 45, 45, and 5,000. And on the transverse direction, we have 7,000 and 25. So in the model, we have 45, 45, 45, 45, and 5,000. And along grid 1, we have 7,000 and 2,500. After verifying the dimension, we can now verify the design groupings. So to show the design groups assigned to the model, so we can simply go to the toolbar, click here on the show or hide information, and then toggle the design group. So once this option is checked, all of the members that you will click will show its design group. So to check easier, we can go to the front view. Let us isolate first the second floor. Right click and show only and go to the top view. Now that the design groupings option is checked under this show or hide information, once we select all the members in second floor, it will automatically show its groupings. So now again, let us confirm if it matches with the plan. So let's take a look on the second floor framing plan. So along grid line A, we have G3 for all of the beams. And along grid 1, we have G5 for grids from grid A to grid B and G4 from grid B to grid C. Okay. So in the model, we have G3, all of the beams along grid line A. And along grid line 1, we have G5 and G4. So that's how you do it. So if you want to continue it to other floors, so that's how you can easily do it. And after verifying the dimension and the groupings, we can also instruct the program to check the model by scanning if we have duplicate nodes, duplicate members, and sliver face. Okay, so to do that, you go again to the member tab and then you click check model. So here in the check model, you just click check. You choose if you want to check all members or just by selection. So for this example, we will be checking all the members. So click on check, and then a message will appear in the message window here in the lower left of your screen. So it says here that there is no duplicate member. So let us proceed to the checking of the nodes. Again, click check, and then on the message window, it appears here that there is no mergeable point. So for the sliver face, also let's click on check, and then on the message window, it appears here that there is no sliver face. So now that we're done doing the verification of the geometry, let us now proceed to the loadings. So this inputs are designer's discretion. So only for discussion purposes, I will be using these values. And of course, I'll be presenting their references from NSCP 2015. So let's start with the live load. we use the minimum design loads from NSCP under Table 205-1. We can see the table that contains the minimum design loads suggested by the codes. So for the roof, we have 0.6 kPa, 1.9 for the classroom, and 2.4 for the toilet. So we can verify that here in Table 205-1. So for the live load on corridors, we have 3.8 and 4.8 for above ground and on ground respectively. So let's go back to the model and let us verify if the loadings correspond with the design criteria. So all of the verifications that we will do, um, we'll do them here in the analysis workstream. So I forgot to mention that the workstream has various tabs. So it contains the display workstream, the model workstream, the analysis workstream, design workstream, properties, and the table workstream. So for the verification of loadings, we will do that here under analysis workstream. So we click on the static loadings, we toggle on the static loadings, and then right click and modify. And then we click here on the load type, and then here we can see all of the predefined loadings, dead load and live load, per area of the floor. Okay, so for the classroom, we use 1.9 live load, corridor above ground 3.8, toilet 2.4, and roof deck 0.6. Okay. So for the dead load, so these are just basically all the stagnant loadings that are superimposed on the building, such as the floor finish, the mechanical or electrical equipment, or I'll call it the utilities. So also all of the things that are attached to the slab and the weight of the slab itself. So since we did not model the slab, so we include the weight of the slab in the floor loads. So again, there are suggested minimum dead loads in NSCP. You can find it on table 204-1 to 2. So if we are not able to reach the manufacturer for the actual dead load, we may use this code suggested loadings. Okay, so for this slab, we are using 125 millimeters thick slab. So to convert that to floor loads, we just multiply the 23.54, the unit weight of the concrete, times the thickness of the slab. So we get 2.9 kPa. For the floor finish, so I found this one in NSCP. So that is the ceramic or quarry tile on 25 mm mortar bed. So that is 1.1 kPa. So we also have the utilities. So this one is an assumed values of the subbation of the utilities that are attached to the slab. So for this, we are using 0.2 kPa. So all in all, we have 4.2 kPa for the floor loads. So for the wall loads, I used the one suggested by the NSCP. So for external walls using 150 mm thick CHB, we use the 2.8 kPa plus 0.48 kPa for the plaster on both sides. So you can find that here. Also on table 204-2. So this one, 0.24 kPa for each side plastered. So times 2, so it became 3.3 kPa all in all for external walls, because we assume that the external walls is 150 mm thick CHB. So for the internal walls, we are assuming 100 mm thick both CHB, both plastered. So all in all, we have 3.17 kPa for internal walls. So since these are in kPa and we are inputting it in beam loads or uniform loads, we have to multiply the height of the walls. So 3.3 kPa times the height of the wall and 3.17 kPa times the height of the wall. So again, let's go back to the model to verify the load unit. So under dead load, we go to the beam load, right click and modify. And we will see that the uniform load is negative 10.5, so that is 3.3 times the height of the wall. Also negative 10 for the internal walls. So you can toggle in it so it will be shown in the model. And if you want to view the values, you just go to the toolbar and then show or hide load value, or you can simply just Control Alt V. So you can see the